Hey everybody, this is Larry. This is week 5 of the weekly premium challenge. Wow, April is almost done, isn't it? Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. Have I done this one? I have not done this one. I only checked just so that I want to maybe do an extra problem because I've been not doing extra problems. But yeah, hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this one. Bitwise or of all subsequent sums. Given an integer numbers, return the value of bitwise or of the sum of all possible subsequences in an array. Okay. I don't think this one is that tricky, but is it? So I think the key thing to know for this one is that for bitwise ORs, it is an additive thing, right? Like, as long as a 1 appears in the digit once, it doesn't matter how many possible places that it has, right? And oh wait, subsequent sum, not bitwise or okay, maybe that's different, because then now this is a terrible example too because of whatever, but because you can get 4 and then that's how you get 7. Okay, fine. But yeah, I think the way that I would think about it is still kind of the same idea. Now that I think I misread it, actually, to be honest, so my apologies. But the sum of the subsequences, right? But that what we're saying is that for each for each bit, we only need one subsequence that has that number, that bit active, right? And so what does that mean? That means that, for example, with one, if there exists, so my first idea might be that we would check it for every digit or every binary digit, every bit, right? Like in this case, we'd say, can we make a 1 anywhere? Can we make a 2 anywhere? And then can we make a 4 anywhere? You know, every bit. Can we make an 8, etc., right? I mean, in this case, you can clearly see how to make a 4. I have to really think about carefulness. Right. Because I don't know that, like the first idea I was thinking of is that maybe we can do some greedy thing with the array for each bit, right? And then just figure it out. But I don't know that it is quite as easy as that. But maybe it is. Because then now we can just think about it in terms of each bit, and yeah. Because okay, so this is my idea, right? Is that first of all, we this is kind of hard for a medium, but anyway. But the first thing that I would do is that now I could say the concept is that, okay, let's say we want to check to see if we can make a 1 bit, right? Like a bit in the 1 position. Well, that's easy, right? We just check to see if there's any odd number in nums. And then now we want to see check there any 2 bits. And then now it becomes, okay, is there a way to create a bit on the 2 bit? And there are 2 ways to do it, right? One is that if any one number has a 2, then we're done, obviously. But also we can do it if we have 2 things in the 1 bit, right? And my hesitance was something about carrying, because if you have like 3 plus 3, you get 6. So then now you get 1, or maybe even like 3 and 1, so then now you get 4, but then now you don't get a 2-bit. Is that good enough? No, I mean, but then now you have this like thing where you have at least 1, because by definition, so then you cannot like no matter, so they only, okay, let me rephrase, or not, maybe not rephrase it, but there's only there's only 4 possibilities of cases, and 3 of them, 3 unique ones due to symmetry, right? And basically this is case 1, right? Can we get a 2-bit? And the answer is yes, right? Because you just add them together, and then now you get 10, which is 2, and 10 in binary, which is 2. So then now we can create a 2-bit in one of the subsequence. And then here, well, we just have a 2-bit array, so we don't have to do it. Here again, we also have a 2-bit already, right? So we don't need to do it. So that means that, and I think we can use this logic in a carry kind of way and an induction kind of way, because then now you could expand this logic to the 4 bits. So I think from that, you can construct it, but it is hard for sure, right? So then here, let's do it, right? So for x in nums, and maybe we have like a f is equal to a counter, but we have 32, just push to, 10 to the 9, fine, 32, right? And then this is just for I in range of 32, or maybe we'll just say b for bits. Yep. Right, so then we do this, and then now we can just carry it forward, right? So what I mean by that is for I in range of b again, right? So possible is going to be our answer. If f of I is greater than 0, then it is possible, right? So then now we make it I, right? The only thing is that then now we also have to carry, right? So then now if I is greater than 0 and f of I minus 1 is, or you don't even need to do it this way per se. You just do f of I, we add it to f of y divided by 2, because obviously you need 2 to match, right? And then that's it, I think. That gives a, oh, well, I maxed out way higher. Oh, wow. Okay. Yeah, I mean, okay, fine. Okay. I mean, so the thing that I missed in this thing is that I do not carry the bits forward enough. So that's basically the thing. Because after 32 bits, f sub I could keep on going, but I just kind of missed that case. That's a good case, to be honest. I just didn't really, I think I was just very kind of locked into 32 bits, but that's actually a very good edge case. But that's the idea, and maybe you could do it like in a slightly less sloppy way, but that should be, and maybe this should be 32. This would be much faster. But yeah, I mean, very interesting problem, very cute problem, very easy to miss edge case. Because basically we're doing carrying, but then I just chopped off the carrying at the 32nd bit, because I didn't expect it to, I mean, it makes sense once you think about it, because the sum of 10 to the 9 number, 10 to the 5 numbers times 10 to the 9 is going to be 10 to the 14, and 10 to the 14 you need a binary bit that's bigger enough for it, which is, I think, like maybe 42 or 43, something like this. But a very good problem, very interesting problem. So what's the complexity here? It's going to be x times b, where b is the number of bits. This is just over b, so this is much cheaper. Or 2 times b or something, or b times n maybe, or something like this. But in terms of the max number, not the complexity. But yeah, that's all I have for this one. Let me know what you think. Thanks for watching. Stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye bye.